I am Brian W. Mulligan, also known as Astrobit.
And I am Sinclaire Manning, also known as Major Merger, and we are here to present you with this month's top news stories in astronomy.
Or at least what we think are top news stories. Yeah.
We're starting off on a sad note and then
Sad
going
note,
up from
but
there.
it gets better from here, believe me. So Opportunity, so our News from Mars Opportunity mission has officially reached the ending. Last month, Opportunity and its twin Spirit landed on Mars back in January 2004. It was originally planned to be 90-day missions. They lasted way longer than that. So Spirit survived until 2010 when it got stuck in the dust, wasn't able to maneuver itself, and lost power. Opportunity was stuck in a very strong dust storm, the strongest ever seen on the planet, or at least that we've been there for. It either got buried or the electronics got damaged. We're not exactly sure, but we haven't heard from it since last June. So NASA said, yep, I think that's it. Aww. But the good news is the current NASA lander on the planet, the NASA InSight lander, or Mars InSight lander, it has finished deploying all of its probes. So back in December, it deployed a seismometer to measure Mars quakes. I got it right this time, for those who remember. So it's measuring vibrations, helping to understand what the interior of the planet looks like. They put the probe placed the wind shield over it, so it's a little shield to prevent wind from blowing it around, and also to keep light, heat from making it expand and contract and cause other vibrations in it. But perhaps more importantly, the heat probe was deployed. This is what you see. So here's the seismometer, and here's actually an actual picture of the seismometer. There's also this heat probe, which you can kind of see the thing sticking down here. It's going to get hammered into the surface down to about 16 feet below the surface to measure what the temperature of Mars is inside. If it's warmer, if it starts getting warmer as you go down, that would suggest that Mars has an internal source of heat like the Earth does, which could be extremely promising for prospects of life or tectonic activity or something like that. So whether Mars is still active or whether it's effectively a dead planet. The hammering's also going to help calibrate the seismometer. Imagine standing a few feet away from somebody who's hammering on something. You can detect that. It's going to give a lot of information about the properties of the rocks that are sitting essentially right underneath the probe. So exciting news coming up. It's going to take another month or so to get that probe fully in place.
All right, so next up, just last month we had a news story about 2014 MU69, or as many were calling it, Ultima Thule. At the time, astronomers thought this object beyond Pluto was shaped like a snowman, with two roughly spherical lobes smashed together, and you may remember seeing a picture of it in the first talk tonight. But the final photos that NASA's New Horizons spacecraft snapped of MU69 during the probe's January 1st flyby reveal the distant object is to be far flatter than originally thought, bearing closer resemblance to a pancake. So the object is about 21 miles long and lies 1 billion miles beyond Pluto's orbit, which is about 4.1 billion miles from Earth. New long exposure images were taken after the spacecraft's closest approach from a different angle than the initial snowman suggesting photos. So with the new long exposures, mission scientists were able to see MU69's outline against a number of background stars, and then by noting which of these stars went dark as MU69 blocked them out, they could map out the object's surprisingly flat shape. So it will take a total of about 20 months for New Horizons to send home all the flyby imagery and measurements that it's taken, so there may still be more discoveries to come. The spacecraft is also in good enough health and has enough fuel to fly by another distant body, so fingers crossed that NASA grants them another extended mission.
Oh, that's exciting. I hadn't heard about that. That's really exciting.
Keeps going.
Wow. The Energizer buddy of satellites. All right, so a team led by John Wise of the Georgia Institute of Technology have suggested a new mechanism by which supermassive black holes might form in the early universe. So there's supermassive black holes in the centers of every galaxy. These are black holes that are probably, or that are millions to billions of times the mass of our sun. There's still questions about exactly how they form early enough in the universe. John's team ran simulations of the early universe, seeing how galaxies form, see how dark matter coalesces. Their simulations initially followed clumps of dark matter as they began to coalesce to form galaxies. While some of the clumps formed stars as we expected them to, the team found that some of the outlying clumps were unable to form stars due to the light of stars in nearby clumps, as well as supernova that were exploding in those clumps and contaminating the clumps that they were interested in looking at. Essentially preventing the formation of stars in some of these little clumps of dark matter. So by preventing the formation of stars, all the gas in those little clumps winds up directly collapsing into black holes, and the black holes are large enough to seed the supermassive black holes that we see in the galaxy, or that we see in our galaxy and in other galaxies. While this is really exciting, but I'm still skeptical. This is not the end of the story. Research done here at UT by some of our colleagues, Volker Brahm, Athena Stacy, Jacob Hummel, and some of the recent graduate students here. For those of you who know them, they have found that the fine details of star formation within these clumps and within the early universe suggest that there's a lot of fragmentation that goes on. Things that we think that are going to be, so initially we thought that the first stars were going to be, 100, 200 times the mass of the sun, and they found that no, there's a lot of fine details that affect this that make them only about 30 times the mass of the sun. This team has not really fully taken those details into account as they were performing their simulations, so I'm not fully convinced that they've got it right. However, if this work does hold up to scrutiny, it's still possible that this is a really exciting leap forward in understanding how supermassive black holes will form.
All right, so astronomers were recently able to make the first detailed chemical maps of the large and small Magellanic Clouds, which you can see in this lovely picture on the left here. And they found that the star formation in both the LMC and SMC has spiked in the recent past after an initial lag. So as the Milky Way's nearest neighbors, the LMC and SMC lie about 150,000 light years away, but it has been difficult to map out their full structure. So David Nedever and his colleagues used the Apache Point Observatory Galactic Evolution Experiment number 2, also known as Apogee 2, survey to obtain precise observations of 5,000 stars in the Magellanic Clouds. So by mapping out how heavy elements are distributed through the stars in the galaxy, they were able to model approximately when generations of stars were born. The LMC and SMC are only visible from the southern hemisphere, and it wasn't until 2017 when the Apogee 2 instrument was installed on the Las Campanas Observatory in Chile that astronomers could complete such a detailed study. So based on the chemical makeup of thousands of stars, Nedever and others found that the Magellanic Clouds got off to a slow start initially, but about 2 billion years ago, the large Magellanic Cloud suddenly started forming 6 times as many stars as it had been. So most likely this uptick in star formation was caused by a recent brush with the small Magellanic Cloud, and they can see features in their structures which suggest the two dwarf galaxies have indeed interacted. So the LMC and SMC star formation rates were low compared to other dwarf galaxies around the Milky Way, but astronomers believe this is due to the environment which they evolved in. So the LMC and SMC are most likely taking their first lap around the Milky Way after spending about 10 billion years building their stars up in isolation, whereas other dwarf galaxies had been interacting with each other in the Milky Way beforehand. So only now, in the last few billion years, have the pair begun to interact more frequently with our Milky Way and one another, which has boosted how quickly they can form stars.
Pretty cool. All right, so we have a new measurement of the Hubble Expansion parameter. So a team led by Simon Beerer of UCLA devised a new method of measuring the rate of expansion of the universe. So they used images of a distant quasar that's been gravitationally lensed. So here we've got quasar, the same quasar, and then all these other bright spots are other galaxies that are nearby, or that are causing the quasar to be lensed. Because the light from the different images takes a very slightly different amount of time to get to us here on Earth, we can watch for outbursts or quiet periods of the quasar and perform a detailed analysis of the variation in the time and the distribution of galaxies that's causing it and all kinds of specific details. There's essentially a 113-day delay. So I don't know which one's the earlier and which one's the later, but one of these, the light gets to us, a third of a year earlier, like 3.5 months earlier. Using these measurements, using the slight delay between them, leads to a measurement of the expansion of the universe. The measurement they found is consistent with that measured using supernovae. This is very promising. So this is an independent method of measuring it. It finds a value of about 72 kilometers per second per megaparsec for those who are keeping track. But this is very, very different than the rate that's measured from the earliest light that we can see in the universe, called the cosmic microwave background. There's been a controversy for about the last 15 or so years, 15, 20 years, as to these two different methods find different measurements. The fact that this agrees with one of them suggests that that measurement is definitely correct. The cosmic microwave background measurement is probably also correct. So we don't think that they're wrong, but this strongly suggests that yes, in fact, there is something causing a change in the expansion of the universe in the earliest times in the universe. Now, in the current era of the universe, dark energy is invoked to explain how the universe is expanding faster over time. Oh, sorry. Dark energy currently, is that better? In the beginning, so we're measuring differences in the expansion of the universe over time. In the current universe, dark energy is used to explain how the expansion is changing over time. In the earliest times of the universe, we didn't think that dark energy would have that much of an effect. But the fact that we're seeing a significant difference between the earliest light that we can see in the universe and the later light that we're seeing from these quasars that happens, a few billion years later, suggests that there is a significant acceleration in the expansion of the universe at early times. This might be dark energy, or this might be a completely new phenomenon that we cannot explain at all. And we need a lot more information in order to understand the details of what's going on. This is different than inflation. So this is not inflation, and this is probably not dark energy. But who knows, they might all be the same thing. So stay tuned.
All right, last up is Astronomy Not in the News, where we highlight a story that maybe didn't get as much coverage as we thought it deserved, but we'd like to tell you all about it here. So a record-setting orbit of an ultra-compact X-ray binary which harbors an accreting millisecond pulsar has been discovered. And if that made no sense to you, do not worry, I'm going to break it down right now. So on the left of this artist rendition here is an artist's impression of the system. But so it consists of two stars, a very low-mass white dwarf on the left, and a pulsar in the middle. So a white dwarf is the stellar core remnant of low-mass stars like our sun after they've exhausted all their nuclear fuel. And pulsars are neutron stars which are born during a core collapse supernova, which occurs when stars much more massive than our sun can no longer withstand their own gravity after nuclear fusion in its core has ceased. So they are pulsars, that is, are among the densest objects in the universe, as they have 1.4 times the mass of the sun, crammed into a sphere roughly 20 kilometers in diameter, so about the size of a large city. As these neutron stars rotate, we can see periodic pulses of radiation if we're lucky enough that it's beamed towards our telescopes. And millisecond pulsars are particularly special compared to ordinary pulsars in that they are typically spun up by accreting material from a nearby orbiting star, which in this case is the white dwarf. So this system, So this system is called J17062-6143. I'm hoping for a better name soon. And it has a white dwarf in a record-setting 38-minute orbit.
Wow.
Yeah, wow. Around a central pulsar, which rotates at about 9,800 revolutions per minute, which is generally about the same speed or faster than your kitchen blender rotates.
So the white dwarf has gone around like 4 times while we've been here tonight.
Yeah, this thing's on the move. It's
And this is like a million times so far today.
So the white dwarf and pulsar are separated by only about 186,000 miles, which is less than the distance between Earth and the Moon. And these data were taken with the newly commissioned Neutron Star Interior Compositions Explorer, which is also known as NICER, which is, gotta love acronyms, which is an X-ray instrument on board the International Space Station, which is pretty cool. The author's findings are based on the analysis of recurring X-ray pulses produced from hotspots near the pulsar's magnetic poles, formed from the white dwarf's infalling material, which collects into an accretion disk around the pulsar, which is what you see in this artist rendition. So future NICER observations of the system will allow astronomers to look for enormous helium-powered thermonuclear explosions on the surface of the neutron star. This is a very extreme and rare object. Very interesting. Wow.
Pretty cool. Very cool. Actually really hot.
Really hot. All right.
All right, well, that is all the news we have for you for, what month are we in? February. 2018.
Thank you.
2019.